Welcome back to the Acreon tutorial series where I'm looking at the quarter car wheel model, where I'm looking at H infinity control, which was just introduced in the part 3. And now we're looking at the observer side, or the dual problem of the static weight output feedback. It's posed, and again, in the similar way as H2, where I separately am synthesizing the control gain K, and then I am synthesizing the Leuenberger observer gain L. This side of the coin, where performance metrics are on the H infinity norm, which is that if I scroll up a little bit, we had a performance criteria of minimizing the body acceleration, the suspension, like stroke essentially, or that length between the displacement, the perturbed length between the body and the wheel. Um, and then the road handling, which takes into account this road disturbance that's entering the plant, as well as penalizing the control effort. And so the dual side, we're looking at that C that was composed in part 2 when we looked at observability, and that had the analogous approach here with the difference in the suspension stroke, if I can just find that C here. And then we had the body velocity too, which would just be an integration of if we had, say, an accelerometer on the body, just integrating it once, and then we get the velocity component of the body. So say we have these two, well, it'd be kind of the two separate, say, sensors that are measuring the perturbation about the body and the wheel, and then we're measuring the difference there for the C, and then we have the body velocity there. And really briefly, I just wanted to clear up perhaps an area that could be confusing, and I was a little too cavalier on the similarity transforms introduced in the static or the state, sorry, this H infinity state feedback with the static weighting. So if we go down to the scaling part here, where I'm non-dimensionalizing and scaling, this was a little bit different than what I was doing in H2. This here, so we're pushing forward the barred space, right? This barred space is the non-dimensionalized scaled units of our vector, pushing that forward onto A, which would be in Z, the normal component, or the coordinate vector here, Z. Now, pull back SZ inverse would pull back Z onto the Z bar space. Okay, so then that's why we're in this DZ bar D tau. So that's a similarity transform. However, this part here is not. So we have this other part here, this scaling on the input space, which is made up of this exogenous input and the control effort. And that's in the barred scaled and non-dimensionalized space. We're pushing that forward onto B. So we have R and U. B pushes that onto now this. We're pulling it back here with the Z inverse, right, to get it into the barred space where we get the DZ D tau. Okay, so it's a little bit of ensuring that the mapping and the coordinate systems are sane, such that we are playing between these two coordinate systems in a homogeneous and linear way. And yeah, and I was just a little loose. This is a similarity transform. This is just moving between two different coordinate systems. It looks like a similarity transform with the push forward and the pull back, but just note we are working with two different coordinate systems here on these three, actually, for the B, D, and C. And then A has the similarity where it's still in the same Z and Z barred space. Cool. And let me see, I had one more note. Yeah, the WQ here. So this is going to be used again in a similar manner when I have the dynamic compensator. So this is actually going to be pulling back the SP. So that's the performance vector, right? We're pulling that back and then applying it by our performance scaling, which was here. So this was this performance scaling in acceleration, the displacement of the suspension, the road handling, and then the control effort. And then that's that WQ. So later, when I am doing the H infinity norm metric, which was similar to what was performed in the H infinity state feedback here, where we were analyzing the passive and the active H infinity norm as a frequency spectrum. So as that, if we go up to the equation here, as this transfer function is evaluated over j omega, which was basically formed in this log space here, this grid for the scaled frequency and frequency grid, we ensured that indeed the certificate that we received back from the H infinity LMI problem was a least upper bound on the worst case gain from the disturbance to the performance output. Okay, cool. So that WQ will be used for the physical side. So this was again in the synthesis or the optimization space, this barred space. And then the dynamic compensator will be analyzed in the physical space or the physical units. And that's where this WQ here is going to be. Man, WQ is above. Here, that's where this is going to be used again. Okay, cool. All right, so moving forward here. So we have the observer side, which is the dual problem. And so we have the C, right? And this is the vector on the output side. So we have the perturbance of the body subtract by the perturbance of the wheel. We have the velocity of the perturbed wheel state. And then we now have these two noise channels that are additive. So the suspension side and the velocity. Okay. So we have now the road disturbance entering the plant, and then we have the sensor noise that's entering the output of the output measurement side, right? So again, we're asking to reconstruct the state Z hat such that we're minimizing the error of that reconstruction. And that's where this H infinity observer comes into play. The difference, though, here is that we are minimizing against the worst case. Again, the same gain. So we're actually going to be jumping ahead a little bit here, but from D to EZ. So the worst case gain of the transfer function, again, on this output side from D to EZ. EZ is that what would be the actual plant state minus the estimated Z hat state. And our disturbance vector is made up of the road disturbance and the noise of the suspension sensing and the velocity of the body. So, okay. So then just repackaging some things. So the BD in this state, in this circumstances is again similar to the carpool side where we have the two. Well, it's basically the BW here for the road, right? So the road disturbance there, and then we're not acting on anything on the noise side, but the noise is entering the plant on the feed through here. We're feeding that through, so that's on the D. It's a D pushed onto the Y space or output. This is our normal, state space equation for the state update, state dynamics, and then the output here. And then this is our estimated here. So we have the Z hat dot, and we have a similar thing as before with the Leuenberger observer times the difference between Y and our CY Z hat. And that is from, so this was our CYZ plus N. This is new, or eta, new, Y minus CYZ hat here. So that's what the Leuenberger observer is acting on to produce a Z hat. And that Z hat, if you remember, is what's actually going to be acted upon on K because there's no reference, right? It's just disturbance rejection at this point. Cool. So that's our Z hat dot now. And so similarly, we have internal state dynamics now for the error. So we have EZ dot is equal to Z dot minus Z hat dot. And so we can repackage things to be factored in this nice version here. And then we substitute the variable for EZ. And then we have D on the outside here. That's the same. And so this is our EZ dot. And then for the transfer function, I wrote it on my whiteboard here, but it's similar to the what was it, the disturbance road to the performance output, except that we don't work with both of these equations. We can work with EZ dot directly here because we have the EZ and the D, right? So then basically we're getting the EZ over the D in the Laplace transform, right? So we have this as a function of frequency, right? So then we have this on the front, and then which would be, this needs to be invertible, and then multiplied by the BD minus LD YD. Okay, so the observer solves the minimum worst case reconstruction gain of that transfer function. So we're minimizing the Leuenberger L such that this H infinity gain of the disturbance and the reconstruction error is less than our least upper bound gamma L. And that's our performance objective. And the LMI is set up again in a dual problem, but it looks similar to this. It's not obviously one-to-one. It's going to be different, where the transpositions and stuff like that is going to be a little bit adjoint. But it looks similar to that problem. We're just looking at the dual observer side of things for reconstructing the state. Okay, so in a similar way as the state feedback, I'm doing observer scaling with the this generalized plant. And so now we have the disturbance channels that include the noise. And so this is just 1 sigma. And this was just the scaling for the barred EZ to get back to the E bar. So we can see the time of the observer reference is a little bit different to get on the order 1. That's still the goal here, is to get it on order 1 for nice numerics on the solver side of things. These are just packaging in the matrices above. So the D observed disturbance, B observed disturbance, D measurement disturbance. And then this is the scaling values that are being used here, okay, for road, suspension travel, and body velocity noises. The measurement scale values are here. And then we package those into the scaling matrices to relate the barred space into the normal perturbed coordinate space. I just walked through these 2 scalings. So then these are the scaled A, B, C, D. Let's see what else is going on here. So then we're packaging these, the C observe and the D observe, together with the V stack, so they're on top of each other. And we could see that on the full observed scaled are on the order 1, which is what we want for the solver. And again, similar as the state feedback. And so this is showing, I'm not sure if I did it above. I don't think I did for the gate, the controller gain, but for the Leuenberger observer, the controller gain is obviously, it's very similar to this, just a little bit different. But so we have this barred L that we're synthesizing, right? That's the object that we collect from the convex optimization problem. And so that's the algebra that is bundled into this L. So then we can invert the mapping here, right? So we get 1 over T observe, which is that reference of the up above. And then reading it from right to left, we have with pullback on SY, that gets it into the barred space, L bar, and then we have a push forward on the Z. So that gives us an L. And so the poles are now the estimator poles with the L from that inverse map. And we can, we're also solving, sorry. So we're solving with the scaled variables. We get really nice solver convergence and very fast iterate, like 7 iterations, which is really, 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 really nice. So the LH infinity scale gain can be seen here. The physical gain is down below, which is much larger. The observer poles are on the left half plane. They have complex conjugate pairs. And then I'm going to plot that below, as well as the state feedback as well, because I didn't plot that above. And I'm going to plot the dynamic compensator with the plant as well. But before that, so the observer error realization and the H infinity norm. So this, we're going to just ensure that the same certificate holds that we introduced above with the state feedback side of things. So our closed loop error reconstruction, A bar is this, and then likewise with the B here. And then the H infinity norm is the same sweep over J omega. So we're still going to use this estimate H infinity norm. This is just the sweep here for the grid. And then this is just repackaging A, B, C, D in such a manner that we can evaluate the observer error realization with the H infinity norm metric, and then ensure that it is less than this gamma L up here, because we're in the synthesis, we're in the optimization space, this barred space. And so with the units here, radians for that tau observe, which is that referenced T observe above, we are good, right? So the observer norm bounded by gamma L is true. Perfect. Okay, so last bit before doing some pole plot analysis and stuff like that, we're now going to package it into a dynamic compensator. So that's again in the similar way as before with we have the control gain K. Now it's operating on the estimation of Z, which is produced by the Leuenberger L, and they're both operating on the H infinity norm metric. The H infinity norm of the observer uses the CY, and then the state feedback has the performance output ZP that we did before. And so this is our state dynamics, our plant dynamics under the state estimation feedback here. The measurement CYZ, and then we have the additive noise on the outside. And then Z hat dot, so that's the observer dynamics are enumerated here. And then, so now we can package it into the, basically the plant compensator interconnection. Did I see it? No. Yeah. Okay. So then this is again similar. So we're bundling in the dynamic compensator with the full plant compensator interconnection that is posed in this manner, and that's just packaging together what the Z and the Z hat are respectively, and then this is just output feedback A. This is output feedback B, and that's actually going to be below. But did I rewrite this twice? No, I didn't. Sorry. So the A compensator, B compensator, C compensator, D. This is our compensator here. Yeah, so I don't think I wrote that. I must have clipped out somewhere. But anyways, so the A side would be A plus BU, K, H infinity minus L, H infinity, and then CY. That's this part here. This is the plant interconnection, so I need to update it so this is portrayed on the markdown. The B side would be LH infinity, C would be K, and then the feed through here is just zeros. And so here's the compensator poles. So you have all left half plane. This is just printing off the compensator itself. And again, this is in physical units, right? Yeah. Let me just double check. Yes. Because we're pulling it back here. So that's our LH infinity. So that's in physical units. And then before I had K, we'll just double check to make sure that is true. We have KH infinity here. Yep. So we do the inverse. We do the pullback scaled and then input scale. So in a similar way as, I didn't write it down, but in a similar vein as this guy here. Cool. But the one difference here is we don't have a time. So the T ref above, that doesn't impact K. It does impact L because we have the aerodynamics. And the aerodynamics is a function of a time. So that's why we have this new relation to the time and that tau mapping on L. We don't have that for K. Okay, I think I cleared that up. So, all right, we did this. And now, so for the plant compensator interconnection, so we have K and L, and those were two separate H infinity subproblems. I am not doing it joint. Again, like the H2, I don't have that set up in my backend. You could imagine a space where you have concatenated the bilinear. If we go back up to the problem for state feedback, you could imagine the dual problem just being a further concatenation of these decision vectors or variables. and mapping that back into the coordinate space that we're doing analysis on for the K and the L. So I have Q, Y, gamma here for the state feedback for H infinity. You can imagine the same thing for the observer side. It would just be a bigger problem. However, I kind of like this representation more, and you still get the linear superposition principle holding. Just note though, it's not going to be like the same joint optimization certificate, because we get two separate certificates for each one individually. Anyways, I could probably do a joint one later or something, but anyways, all right. That's kind of what I'm alluding to here. So we don't have this joint gamma here certificate for the joint compensator. So that's why there's these partial checks now. So we did the check for state feedback, we did the check for the observer. And so together we can do the same H infinity norm. We don't have a certificate to check the least upper bound by, but we can see what the peak gain is in physical units too at a physical frequency. So we can see where the peak is of the compensator, which I'll do below. And that's where I'm doing these the mappings back to get the physical K, the physical L. Okay, so it is here. Sorry. So I do have K here. That's what was described above, and then we have A of the output feedback, B of the output feedback. And so now we're getting into physical state, input, and time coordinates. So then this is mapping the disturbance bar back to D, the performance on the Q back to the ZP, and then this was that WQ that I mentioned above. And so then we basically compute this norm here from the road disturbance, from the noise channels on the suspension and the body velocity to the performance output H infinity norm. So that's what I'm evaluating here, that transfer function. And the physical performance can be recovered with this Q, this relationship here with ZP, inverse pullback on the performance scaling that we proposed above, and then SP pushes that forward onto Q. Okay, or the Q space, I should say. This is setting up now the observer-based closed loop system. So we have A closed loop B, C, and D, and that is going to be what was here. So skipped ahead a little bit. That's what this is. And so we have the observer-based closed loop system, and then our poles. And then that's where we're using the WQ to get the CZDZ of the output feedback from the WQ that was here. So that inverse pullback on the performance and then pushing it onto the performance scaling for that WQ. And then so similar function as before, where we're sweeping over the frequencies for estimating the H infinity norm. We're using the output feedback A, B, C, D. Note that the B and the D are being mapped with the SD and what did I write down? So we have S observed disturbance for the B, and then S observed disturbance on the DZ here. Yeah. Okay. I don't know where the B was though. Should be the same map though. Anywho, it should be the same map because that's still a function of the input there too. And we're feeding through there. So we have a map and a feed through. And we have that scaling on the disturbance channels for the R and the noise. And then the frequency grid, I think, was, formed above. So that's where our estimation H infinity norm here is. So we have the peak gain, and then we have the peak frequency. So let's see what that looks like. So here's our compensator. So closes the plant plus compensator poles, and everything looks left half plane. We have the max closed loop pole real part minus 1.3. And here's what I was getting. So this was the disturbance. It shouldn't be barred here though. This should be in physical units. So don't think it should be in Bard. Although, yeah, this shouldn't be in Bard, but that's the transfer function here from the disturbance to the output performance channel. And then this would be, so it's 0.0133 something, right? That's our gain. And then that's at peak frequency of 56.43 radians per second. All right. So the last plot here is going to be essentially analyzing the full state feedback, the standalone compensator, and the plant plus the compensator. So we have the closed loop poles, we have the compensator poles, and the observer based poles. And that's from plotting all three. So we can see that the full state H infinity feedback follows the plant plus compensator pretty well. We have the diamond blue guy here. We have the plant plus the compensator with this green circle dot, and then the standalone compensator with these orange X's. So the plant plus compensator is pretty good. So, we have pretty good authority in the left half plane here in terms of stability. And we also have the disturbance rejection based off the worst case disturbance from the road input, and also incorporating noise in the sensing channels now, which is pretty cool. So, and I haven't set it up quite yet, as you can see, but the next part is going to be the dynamic weighting here. So if I scroll all the way to the top, next part's going to be this. So we just covered H infinity observer static weight output feedback. Next part's going to be the frequency shaping of the H infinity performance, followed by the mixed sensitivity. So this next part will be interesting because instead of just having it be static weights, if I go to scrolling down here, instead of having it be static weights where we're just doesn't matter about the frequencies, like that's just going to be constant. We said and are going to augment the plant such that we can shape the performance criteria across frequencies, and that kind of gets us like a little bit of a CISO, or single input single output kind of mindset, where with like PID tuning you can kind of get a nice like loop shape in a certain way. However, we're kind of loop shaping the objective criteria. So if I go up here, we're basically shaping this. So we're kind of shaping how R impacts the plant with U, and then these performances here, WA, WS, WT, and WU. We're shaping that as a function of frequency, which will be cool. So that'll be the next part, and then I'll wrap it up with mixed sensitivity and then compare all, so the static to the dynamic H infinity to the mixed sensitivity, which the mixed sensitivity will be a little bit different because we're actually going to look at the closed loop system itself and then break out different transfer functions of the closed loop system. So it'll be like the sensitivity, complementary sensitivity, and how the input affects KS, right? Yeah, that plot or that transfer function. Cool. All right. Well, thanks for watching. Appreciate you tuning in. And I'll see you in the next one. Thanks.